Okay, so it is 6 o'clock in Germany, so time for this week's EMinar. So welcome everybody to the second talk in the third season of the EMinar. Today we have Johannes Stoll, and he's talking to us about semi-airborne electromagnetics using multicopters. I already had a quick glance at his presentation, and it looks really interesting, also going into some of the issues with noise and how to calibrate things. But before we head off, a few reminders and announcements for the upcoming seminar. So you, or most of you probably know, if you hear already, that on MTNet under the EMinars page you can see the upcoming EMinars, and you can also watch previous EMinars, not only from this season, but also from the previous seasons. And if the authors have allowed it, you can also download their presentations. So I think that's a valuable resource that's been building up over the last, well, now more than 2 years. You are in a webinar. I mean, by now we're all seasoned Zoom users, I suppose. Maybe the main thing is that here we try to collect all the questions in the Q&A button or sort of function. So that will then be collected, and so far we've always handled questions in the end, and that has worked very well. But if there's a really urgent question, you can also ask questions in between. There's also a chat function. Usually we use this just for other things that are not questions. If you really want to tell us, okay, whether the voice it cannot be understood or something like this, you can use the chat. And if you really think it's easiest to speak, you can also raise your hand, but we have to manually enable this. Other than that, it should all be really straightforward. And in the upcoming weeks, we have Paulo della Aversana next week. We're talking about integrated electromagnetic methods supported by machine learning for risk mitigation and exploration geosciences. So integrated EM from an industry perspective. And the week after, nope, there was another one. I think it just disappeared. So sorry, if you want to know what's after that, you have to go to the EMinar webpage. So this week, as I said, we have Johannes Stoll, and Johannes is the founder of the MGT GmbH. Johannes, what does MGT stand for? I don't think you explained this here.
Mobile Geophysical Technologies.
Mobile Geophysical Technologies, and that has been operating in 2011, and yeah, has been focusing a lot on airborne sensors and multicopters, and doing EM based on drones. And yeah, has been active in a variety of settings: mineral exploration, environmental, UXO, and also a variety of countries or regions, from Europe to the Middle East, Asia, and Americas. And I think with that, I'll stop sharing my screen and hand over to Johannes.
All right. Good morning, good afternoon, and good evening. It's a big pleasure to be a presenter on this platform. Today, I would like to speak about I would like to speak about drones in geophysical exploration. I slightly changed the title of my talk today because I also want to include airborne magnetics. I think it's important to understand the drone geophysics technology. And if you want to develop this, you easily get into a position to recognize that this is a quite complex system. And I want to explain to you why it was, for myself, very difficult to develop it from scratch. Second, if you ever put a sensor on a drone, you will easily understand that there's a lot of sources of interference generated by the drone itself. And I will show you some slides of findings I have gathered in the last 12 months. Sensors must be small and lightweight, which was not the case in the beginning. So it requires some skills and efforts to choose the right sensors for applications on drones. And I will show you the sensors I'm using to do drone-borne magnetometry and also drone-borne electromagnetics. And finally, I would like to show you some personal ideas about future trends in geophysical exploration. So, drone-borne geophysics. I think drones are a link between ground geophysical measurements and traditional airborne measurements. As I think all of us know that ground measurements are limited to the size and productivity per day. The size of the area is very small compared to airborne geophysics. On the other hand, airborne geophysics was originally designed for wide area mapping of geophysical parameters. So I think or the initial idea to develop drone geophysics 10 or 15 years ago, already in 2008, my initial idea was to try drones and find sensors to integrate them on drones and close this link between ground and airborne geophysics. But it became clear from the very beginning that this platform is very complex. The reason is there are a lot of different kinds of platforms, rotary wing, fixed wing of different sizes and payloads. So in order, especially to do commercial projects, it requires to carefully select the right platforms for the right job. And the type of the platform depends on the size of the area, of the total length of flying kilometers, because it's clear 40,000 or 100,000 kilometers cannot be achieved by a drone, not by a mini drone, multicopter. The flight altitude is also a very important parameter, and it turned out that using laser altimeters, drones can be flown at a very close over ground. If it counts, it can be flown 1.5 meters above ground. Also, the terrain and the environment is very important to consider if you ever plan a drone survey. Usually, if the terrain is very rough or covered by dense vegetation, high trees, measurements on ground are usually not possible. And traditional airborne geophysical measurements using helicopters or manned aircrafts cannot fly as close as possible over the ground, but drones can do that because they follow a digital terrain model. So drones can be or were successfully applied in areas where the accessibility of the terrain was difficult or not possible by foot. But it's very important to note that for commercial projects, only the economic viability of an area platform will do the job. If the flight time, for example, of a drone is too less, you will not be able to complete a project in a given time. So I would like to talk about complexity. I think drones comprise a lot of different key developments which were developed in the last 3 or 4 decades. Especially the introduction of low-cost mobile PCs or smartphones helped a lot to develop a computational power that allows to run high-definition navigation software on a drone. Second, the worldwide network of satellites, GPS satellites, only with these GPS satellites made it possible to use drones and fly autonomously. And in the last decade, the number of drones, of commercial drones, increased over the number of military drones. I don't know whether this is still true, but 10 years ago, in 2012, more commercial drones were produced than military drones. And in the last decade, a lot of effort was undertaken to develop so-called drone formation flying. The increase of computational power and also the development of remote sensing and imaging sensors, cameras, were key also for the development of applications for mini drones. A lot of companies were founded to offer services using LiDAR or photogrammetry and other services. In geophysics, it was very important to understand the concept of array techniques, because drones usually will not fly only along lines. They will cover a whole grid of lines of very dense, a very dense grid, which make it superior, for example, over ground measurements. Also, the sensor technique has increased a lot. In the last 10 years, almost all manufacturers of geophysical sensors developed sensors with much less light and less power supply, which is important because you want to avoid to carry heavy batteries on board of a drone. And also the concepts of airborne electromagnetics were crucial for the understanding of the development of airborne electromagnetic methods on drones. Last but not least, most important and also very critical is an understanding or the development of 3D numerical modeling and inversion codes. For my company, it was very difficult to find software that allows full 3D numeric modeling inversion because, of course, there were a lot of codes, but these were owned by a lot of people. So this is one or the biggest obstacle to use it commercially. And for sure, in the future, we will see a lot of applications using artificial intelligence concepts and virtual reality. So this was the beginning. In the beginning, there were no mini drones, no really commercial mini drones. Of course, there were prototypes, but they couldn't be really used in commercial projects. So I looked around in Central Europe, and I found a company located in Lucerne in Switzerland, who was a startup company from the University of Lucerne, who developed and manufactured a helicopter drone. The takeoff weight is 75 kilogram, and it's driven by a two-stroke fuel engine, which allows to fly up to 90 minutes. And also interesting at that time was that it could lift 15 kilograms. But at that time, for my company, it was impossible to purchase it or acquire it because it costs 200,000 euros. But they were very interested to support my work and to develop geophysical concepts to be deployed on their helicopter. And our first project, commercial project, was in Kahramanmaraş in Turkey after a collapse of a coal mine, which buried the entire infrastructure and also 11 people. And we were asked to try to locate either the people, which is unfortunately was not possible, but we were able to locate the entire infrastructure using a flux gate sensor. On the right picture photo, you see the same helicopter from Switzerland, already carrying a data logger from Metronics, ADU-07, and a SHFT sensor to measure the electromagnetic field, the induced field in the vicinity of a gas pipeline, a metal pipe, which was a pilot project to develop EM methods on drones. But at that time, the logger and the sensor, including the suspension, was more than 12 kilogram, I think 13 kilogram at that time. It could be carried only by this type of drone, not by a mini drone. But time goes by, and a lot of companies were founded in Germany who offers solutions who offer mini drones. These were much cheaper than the big drone, but still 40 kilo euros. It's this quadrocopter from Microdrones, was designed to fly very long, up to 40 minutes. So the total weight, the maximum takeoff weight of this drone is 5 kilograms. It's battery driven and can lift a payload up to 1 kilogram. At that time, I already owned a flux gate sensor system which weighs 950 grams. So it was possible to integrate it and do first commercial projects with this system. I also integrated my sensor, my flux gate sensor, into a fixed wing UAV, the S-180. The wingspan is 180 centimeters wide. The takeoff weight is also 5 kilograms. It's battery driven and can fly and can stay airborne up to 30 minutes. The payload is also 1 kilogram. And we did several projects on volcanoes and also over iron ore deposits in Western Europe. The costs are lower, much lower. It's only 20 kilo euros. 5 years ago, we developed MGT in a collaboration with a multicopter manufacturer. We developed two different systems, one to carry up to 5 flux gate sensors for wide area scanning of for near surface problems, and a second multicopter which was optimized to carry up to 9 kilogram payload. This helicopter now became a standard in MGT to carry out electromagnetic projects. The X810, X stands for 4 arms, 8 for 8 motors, and 10 for 10 kilogram maximum takeoff weight. Can stay up to 40 minutes, and the maximum payload is 3.5 kilogram, and it costs around 30,000 euros. The other ones, the X825 with 8 motors in coaxial configuration. The maximum takeoff weight is 25 kilogram and can stay airborne up to 35 minutes and can lift 9 kilogram. Costs 40,000 euros. Here you see the calculated endurance versus payload. And I show 3 systems provided by MGT. Single MAC system. Penta-MAC means 5 sensors, and the EM system, which weighs 6 kilogram. So you see, with increasing payload, the endurance decreases according to this function. And but this function corresponds with the maximum endurance until the battery is empty. So for safety reasons, we always give 15 up to 20% safety margin to do a safe job. Now about noise. The motors usually used on drones are brushless motors with many poles, and it's important to understand this concept because it's the main source of noise for all geophysical sensors. Usually, these motors are characterized by these numbers: 36 and 42 poles. Then 100 kV, it's a number that describes torque of the motor. As small as a number, as big as the torque, but also as slower the rate of the motor. Here's the principle. Here, yeah. In principle, there are 3 coils and a rotor with a magnet, which is rotated. These coils are controlled by sinusoidal or trapezoidal waveforms, which feed the coils with current in order to force the magnet to rotate. And it's very important to understand that the voltage which is applied controls the speed of the motor. In the formula above, I give a very simple relation, which involves the kV value describing the torque, the voltage. It depends on the battery, type of battery you are using. Usually we use so-called 4S batteries because there are 4 cells. Each cell has a voltage of, because it's a lithium battery, a voltage of 3.7 volts. So 4 cells have a voltage of 22 volts times the number of the poles divided by 20. I found different relations, but here I use this relation. So this allows to easily calculate the maximum rounds per minute for a given electromotor, kV and voltage and number of poles. So in order to control the speed of the motor, because this is necessary to fly a drone or to operate a drone, the voltage has to be controlled. And this is done by so-called pulse width modulation. This pulse width modulation has usually a center frequency around 15 kilohertz and allows to control the voltage of this trapezoidal waveform. But the rotation rate of the motor and the number of poles are critical for the generation of generate an interference with geophysical sensors. Here I show a noise test I have done on a test stand where the drone was fixed. And here you see the onset of the motor of the drone. The motors were activated, and we also see a change of the total magnetic intensity of more than 150 nanotesla. The distance was 1 meter or half a meter. And it's interesting if you plot a spectrogram of the spectrum of this time series. It's interesting to see that there are several frequencies generated, or this signal, this noise train is consists of signals of different frequencies, which change the frequency over time and also spread. So once the motors are shut down, the total magnetic intensity returns to its previous value. These measurements were done with my flux gate sensor. I also did measurements, noise measurements at the same time with my 3-axis induction coil sensor. And here you see the time series of the vertical magnetic field and the spectrogram. Here is the onset. This is in millivolts, not in nanotesla. Here you see the noise when the motor stands still, and here is the onset of the motor with increasing amplitude, noise amplitude with time, and the effect is similar. Here you see the generation of a distinct of signals of distinct frequencies, which change their frequency with time. And it's also interesting to follow this line, which suddenly occurs here. It's not visible before at earlier times, but it starts here. And this is around 15 kilohertz. And this is exactly the center frequency of the pulse width modulator. And it's also interesting to see that there are side slopes of this center frequencies clearly seen here. The other lines here, the other lines show the signal of remote, very long radio of radio transmitter stations transmitting in the VLF range between 10 to 30 kilohertz. This maybe is from Sweden. Another one here is from Germany. Here, this one is in Oldenburg, this line. Here I plotted the spectrogram in, I enhance the frequency range between DC and 4000 hertz to demonstrate the change of the generation of distinct signals or signals of distinct frequency, which changes with time as the rotation of the motors, the speed of the motor increases. And there are not only one. There is not only one motor. There are 8 motors. So the signal is a superposition, or the noise is a superposition of these motors. Now about the sensors. I'm collaborating already 10 years with Maxon GmbH in Berlin. They are manufacturers of very, very accurate flux gate sensors. And I use them because they are extremely light. For example, one sensor weighs only 100 grams, 105 grams. And the electronic control data acquisition system weighs a few hundred to 200, 300 grams. So in total, we are well below 500 grams. So on a mini drone, I can afford up to 5 sensors, flux gate sensors, to carry out magnetic measurements. Here you see a photo taken in Norway, where we were on a commercial project for a Canadian mining company. We used single mag, and the sensor is fixed at the lower end of a pole with a distance of, I think, 2 meters. But flux gate sensors have to be calibrated. The reason is the 3 components are not equal physically. So they have to be made equal by calibration. The reason is because we will use Pythagorean to calculate the total magnetic intensity out from the 3 components. But if there is an error, if there is a noise or an error from a scaling error, because the scaling of the 3 components can be different. Also, the sensors cannot be machined to be perfectly orthogonal, 90-degree between 2 sensors. And third, there's always an offset. So for at a 0 magnetic field, we still see a magnetic field, an external magnetic field. So this offset also has to be removed. And this can be done by flying a so-called cloverleaf test. The idea is to rotate all 3 components by 360 degrees about its axis. Of course, on a drone, the vertical component cannot be rotated 360 degrees. So what we do is we, after we have flown one flight pattern, we land and change the orientation of the flux gate sensor and repeat the flight. And using these using the signal or the time series of each component, it allows to calibrate for each component. Here you see in the lower in the picture on the lower right, you see the curves of the total magnetic field over a sphere. If it's perfectly calibrated, the total magnetic intensity corresponds 100% with the surface of this sphere. If not, if it's not perfectly calibrated, the path, the pattern of this corresponds to an ellipsoid. So it's a kind of measure to define the success of this calibration, which I will show you in the next slide. Here I want to demonstrate the results of calibration. When we fly this pattern and measure the 3 components, the vertical component only little changes. This is the green line here. We take off, and fly around. We fly this cloverleaf shaped pattern, but the vertical component doesn't change a lot. But the horizontal components, the red and the blue lines, change after changing the direction of flight at each corner. So we have a lot of changes here. And in case the flux gate sensor is not calibrated, the total intensity we are calculating is changes a lot. Yeah. Here in this case, the light blue line shows the uncalibrated total magnetic intensity, and we easily see that it changes by 30, 40, 50 nanotesla, which is not acceptable. But after calibration, we get this dark blue line. We get this dark blue line here. And the calculation of the standard deviation reports 0.69 nanotesla. Okay, this means we already have a sensor after calibration which shows acceptable accuracy. But it can be further improved. It can be improved because the flux gate sensor consists of coils which induce additional signals if it's moved in the Earth's magnetic field. So, but this effect can also be removed by calculating the so-called motion-induced effect, which is a derivation of each component after time. If we do this, we further can improve the accuracy of the flux gate sensor, which reveals a resolution of less than half a nanotesla. So using calibration, rigorous calibration, airborne calibration, and applying this motion-induced correction, we are able to improve a flux gate sensor and provide an accuracy of much less than 1 nanotesla. So now I would like to present some results of former projects. Here, this is a flight grid collected in Turkey over a gold prospect. Maybe it's interesting to talk a little bit about the performance of this project. The regular line spacing was 50 meters and the tie line spacing was 500 meters. The total distance flown was about 650 kilometers. But it also includes so-called transfer flights. This means flights from the ground station to the next production line, which can be in some cases 1,000 meters. So if you do a lot of flights, we did several hundred flights, you also collect additional kilometers which add to the production kilometers. The terrain was very rough, with changes in terrain, changes of the elevation from 150 meters up to 900 meters. And due to the very dense vegetation, and with high trees up to 40 meters. The flight altitude was minimum 50 meters up to 100 meters above ground. Maybe interesting, it took us 10 days, including 1 day to refly lines to achieve this project, to achieve all data. And in this graph, I demonstrate the performance of our daily production. Blue are the production lines, red are the total line kilometers flown, but only the production lines count. So on 1 day we did up to 80 kilometers. We produce 55 kilometers, but we flew almost 80 kilometers. Yeah, here's the result. Here is a view. This photo gives a view of the situation, of the scene. And here, this shows the total magnetic intensity of the total area. Another application is the detection of so-called UXO, unexploded ordnances. And usually on ground, no one uses only one sensor. Since many years, ground measurements for UXO are done using at least 10, 11, or sometimes 20 sensors, because it allows to measure the gradient and also the total magnetic intensity, which gives a perfect resolution, even if you want to detect very, very small objects in the order of a few centimeters. But due to the limited payload capacity of a drone, it's not so simple to integrate more than one sensor. One critical issue is the weight of sensors, and second, the power supply. But flux gates are ideal for this kind of measurements because on drones, because they are lightweight and the power supply is optimized. Optimized in the sense that we can use very, very small batteries to power up our system. Here you see our Pentamax system, which was applied to UXO problems. And in this picture on the right side, it gives you already an idea how 5 sensors can improve the resolution or the detection of and location of small objects. Because if you would fly only a single magnetometer, it can easily happen that you miss small objects. But with using 5 sensors, you get almost a 100% coverage of an area, and it's very unlikely that you miss an object of a certain size. Here I give you an example. On the left side, you see the total magnetic intensity of an area which was flown with the Pentamax system. I enhance this line. This is 52. I don't know where it is. 30, 38, 7. Here. It's on the left side. You see the location of objects which are numbered, and these are the flight lines and the total magnetic intensity of the 5 sensors. These clearly show changes in the total magnetic intensity, which is in the order of 10 nanotesla, 15 nanotesla. So several objects were detected. Here is an unknown object which was buried out. Other objects were known and identified. This peak was generated by a very heavy bomb at 2.1 meter depth. But we also were able to identify and locate very, very small objects. Here is one which is buried 10 centimeters below surface and has a caliber of 3.7 centimeters. We know there is another one, but it was already too deep. It's almost 1 meter deep, and we were not able to identify it and locate it with our system. But another one here was obviously detected. Yeah, and this object wasn't detected because we didn't fly over it. So as a summary, we identified a lot of objects, and using this graph, we are able to define a detection threshold that holds for our system. And it turned out that using this Pentamax system, we can identify and locate objects of a size of the order of 4 centimeters. If it's deeper than 1 meter, we probably are not able to identify it. Smaller objects, smaller than 4 centimeters, are most likely cannot be identified and located. Now about electromagnetics. We use a super high frequency sensor from Medtronics. It's designed to measure signals over a wide range of frequencies from 100 hertz up to 300 kilohertz. Accurate calibration allows us to go down to 50 hertz or 30 hertz. The 3 coils were built into a very lightweight box, so the total weight of this box is only 1 to 2.1 kilograms. And we also integrated the electronics in a very lightweight box, which measures 3 channels, the 3 magnetic fields, with a sample rate up to 524 kilohertz. And the weight is 4 kilograms. So in total, it's a little bit more than 6 kilograms. We also use it in not only in mining projects, but also in projects where it is necessary to very, very accurately measure the position and the altitude of the drone. So we have 2 sensors which measure the heading of the drone. This becomes very important in areas where the magnetization is very, very strong, because it happened it occurred to us that in one mining area, the magnetization of iron ores was so strong that the compass of the drone was disturbed, and the drone almost crashed. So it's important to have a means that helps to keep the direction independent from a compass. So we use 2 GPS receivers, and we have another one, a high precision GPS receivers, which measures raw data, satellite data, which can be further processed after the survey. And using this high precision GPS receiver and post-processing of navigation data, we are able to achieve accuracy of the altitude in the order of 50 millimeters, 5 centimeters. Now I would like to present you a project which was done earlier this year in North Norway. The problem was to identify graphitic mineralizations in the ground, which are probably associated with tectonic fault systems. And the idea was to use distant radio transmitter stations to map these fault systems, because if the VLF method is known to induce secondary electromagnetic fields, currents, which generate a secondary magnetic field, which can be measured by induction coils. And we used the induction coils from the super high frequency triple from Metronics. And for those who, I think all geophysicists are aware of this methodology, of the very low frequency methodology, which essentially measures, allows to measure the ratio between the vertical component and one of the horizontal components as a phase reference. Because we have 2 horizontal components, we are able to estimate the tipper A and the tipper B. And we also know that, or geophysicists, electromagneticists know that there is a relation between the 2 horizontal component and the vertical component. In layered earth or in homogeneous ground, there is no horizontal component, no vertical component, because the vertical component is only generated or can be seen above surface if there is a change, a lateral change in the electrical conductivity. So we can use these relations to calculate the tipper A and tipper B, which are functions of frequency. And since in this area we were able to measure the signal from several radio transmitter stations, first I was able to choose one transmitter station where the strike direction of the fault system points to the location of the of this radio transmitter. And this was, in this area, it was the transmitter station at the coast of United States, east coast of United States, Cutler, with the call sign NAA. We know from EM theory that only transmitter stations which point to the direction of strike of a conductive strike of a conductive zone, only these signals induce secondary currents in this structure. Another one, which is perpendicular to strike, cannot induce currents in this structure. So using two transmitter stations, it's possible to estimate the tensor of this of the tipper. In the early 90s, Patterson and his team developed a way to estimate the so-called peaker. The peaker is a combination of the first derivative of tipper A plus derivative of tipper B, which gives the divergence of tipper A and B, which is possible because the electromagnetic field is a potential field in the air. And a second characteristic is the peaker is independent from strike, from the strike direction of this structure. So it's an ideal parameter to be used to map conductive structures in the subsurface. Here I show the location of the survey area, which is in the northern part of Norway. And I used the radio transmitter from the east coast of United States, NAA, Maine, and another one from Norway, which is a few hundred kilometers away from the survey area. The survey area is located on Senja Island. There are two observatories run by the Geophysics Institute of Tromsø, which allowed me to get two time series to correct the magnetic measurements. Because our measurements, EM measurements, are always done in combination with magnetic measurements. Yeah, this is the area. It was right in the mountains. Was very cold in February, -25 degrees, which had a strong impact on the flight time of the multicopter because the batteries cooled down very, very fast. So we were able only to fly no more than 20 minutes. And the area was only accessible by snowmobiles, which was fun. Here you see the results. Here I show on the left side, I show the results of the real part and the imaginary part of tipper A and B for the United States radio transmitter, and on the right side for the Norwegian transmitter. Tipper A, real part, and B. And you see that except for the real part of B, tipper B, for the Norwegian transmitter station, only the tipper B, or mainly the tipper B for the NAA radio transmitter station gives a sufficient signal that allows to image this change in electrical conductivity. Yeah. So only the transmitter from United States, Cutler, could be used to detect this change in electrical conductivity, because it's almost perfectly oriented to the direction of strike. Here you see that it's a peaker, an image of the peaker, real part and imaginary part. And I think it clearly images the curves of the change of the electrical conductivity in the subsurface. Here you see several other plots. The in-phase part or out-of-phase part of tipper B for the US transmitter station. The geomagnetic intensity, which also shows a strong change in the magnetization over this contact, and which is clearly revealed if the horizontal gradient of the total magnetic intensity is imaged here. Yeah. And in addition, I use a Karus-Yeld filter. It's a numerical filter which can be applied to the real and imaginary part to image or to represent the electric currents in the ground for at depth. And the application of this numerical filter from Karus and Yeld to the tipper B, real and imaginary part, reveals that the current induced in the ground is increased exactly at the change of the conductivity imaged by tipper A and B. This is enhanced here for to see it better here. Yeah. So last application, semi-airborne EM. This is not a simple measurement because it requires a lot of logistics, because it involves to establish a strong electric dipole, horizontal electric dipole in the field. Usually a transmitter with a power of 10 to 30 kilowatts must be applied. And a second problem could be that the drone flies always between the near field and the far field. So the data, the modeling and inversion of the data requires high sophisticated numerical modeling code, which because it's a near field, the electric the curves of the cable or the characteristics of the artificial source has also been taken into account in the modeling. Yeah. The idea to use drones for semi-airborne electromagnetic measurements was somehow triggered by the DESMAX project. Maybe some of you have heard about it. DESMAX stands for Deep Electromagnetic Sounding for Mineral Exploration, and it's a BMBF funded program. There are several German institutions involved in this, the BGR and a lot of companies and University of Münster, and also the Leibniz Institute for Applied Geophysics and others. So it uses the semi-airborne method, uses a big helicopter from BGR, a Sikorsky, which weighs around 5 tons, 5,000 kilograms, which carries a bird with 3 induction coils inside, and carried on a 50-meter long, or towed by a 50-meter long cable by this helicopter. So the total system weighs around 5.5 tons. The idea, of course, a drone cannot lift a few hundred kilograms. The idea was to use our EM system to apply it for semi-airborne EM measurements. And the pilot project was done in November 2018. Semi-airborne involves injecting current into the ground by a powerful electric source with a wave train, with a certain pulse train, positive, negative. Here you see a wave train, a pulse wave train of 80, a little bit more than 80 hertz, and which produces this spectrum. And this is one of the main advantages of the semi-airborne EM method, that if the rising time of the signal of this pulse is sharp enough, it generates a lot of harmonics, hundreds of harmonics. So here you see the fundamental frequency in this spectrum of this wave train and the harmonics. These are more than 400s. At the same time, a rover drone flies over the survey area. Here you see the wave train measured on the drone with a EM sensor, the super high frequency triple sensor, moving away from the dipole source, electric dipole source, and the amplitude decreases. And this is the spectrum over the 4 seconds. You see the fundamental frequency in the receiver data at 83 kilohertz, and a lot of harmonics. And all these harmonics and all these frequencies can be used to estimate a transfer function. The transfer function is nothing else than the ratio between each of these lines in the spectrum, the harmonics, divided by one distinct line of the source spectrum. So we have the transmitter spectrum and the receiver spectrum, and we can build the ratio, the transfer function for selected source frequencies. So if we do this, the field data consists of the vertical and the horizontal field data for a given frequency, which is plotted over the grid, and for specific measuring points, the transfer function can be calculated. Here you see an example of the transfer function for several distances, for 50, 100, 200, 300 meters away from the electric source. And because it's a complex number, we get a real part and an imaginary part, and it follows. It always have this characteristic. Yeah, the real part has to convert against a fixed value at large distances, and at very low frequencies it has to approach a fixed value, and the imaginary part must become very, very small, 0. So we in a project, in a semi-airborne project in Germany, we were engaged by a water company from Hamburg to use semi-airborne measurements to discover a so-called paleo channel. A paleo channel which was created during ice, or at the end of the ice age, and which is supposed to carry a lot of fresh water. So for big cities, it's very important to know such freshwater resources. So one idea was to use semi-airborne measurements to identify or to study the existence of such a channel, and to get information about its extension, horizontal and depth extension. Here you see an example taken by SkyTem in Denmark, which gives an example of such a paleo channel. The 3 upper panels show the electrical conductivity with depth. So with increasing depth, this becomes thinner, and here you see a cross section, which shows that this is almost a perfect image of conductivity image of a paleo channel. This is a flight area, and here you see all different flights which were undertaken to measure this area. The area is about 1.5 square kilometer wide, and it took us 6 flights to achieve all data. It was very, very difficult from a logistical point of view, because first we had to get a permission to fly there. We had to ask the airport authority, because there is the Hamburg airport is nearby, and there is also a hospital, and we had to make special arrangements to allow helicopters in an emergency case to fly to the hospital, to land at the hospital. And last but not least, there were a lot of observers, pedestrians, who asked a lot of questions while we were flying. So it was very, very difficult. to do this project, and it took us 1.5 days to complete the measurements. The project is not finished yet, but I'm collaborating with NASA McBell, one of the authors of, or the developers of ModEM, and he provided us a first example of all the data, which I want to show you in a series of slides here, from the top down to about 200 meters. And red is very conductive, blue is very resistive. And we see that especially at the border of the grid, we cannot really trust the model, but maybe in the center. You see that, as a result, I think we can conclude that there is a area with at shallow depth within the first 100 meters, which corresponds to an area of moderate conductivity, which could correlate with a so-called paleo channel. But there are other effects which we cannot trust in this model, and we are now re-evaluating or reprocessing the data and re-evaluating the model. So I come to my last point: future trends in electromagnetic in geophysical exploration. I want to mention the work of Brian James, a good colleague of mine, who had an idea to use drones to enhance the signal from the subsurface. It involves not only one transmitter or two, it involves many transmitters laid out on a regular grid, on a regular spacing, and activated. But it makes it drones very necessary, because each transmitter location or each source position has to be flown one time. So if you have 10 or 20 source positions, the same area has to be measured 20 times. This cannot be done by walking anymore. And I think this is a very good reason to involve drones in this kind of measurements. Brian calls this interferographic transient electromagnetic imaging, and he will introduce all of us I think in January. He will give a presentation where he will introduce us into this methodology. Second, it's known for all exploration projects that the owner of a license area has to make a very hard decision at some point, whether to drill or not to drill, whether he should go forward and exploit the commodity, or and he has to make a decision about money, and his intention is to spend some money at the latest point, at the latest time possible. what he needs is the best information about the subsurface. And I think drones can help to improve the data quality, and especially the number of data and the size of the area, to give him the best information for his project. But it's not only the number of data, it's also the quality of the model. So in the future, I think it will become very, very necessary to include all available information in our numerical models. Second, so the costs of a ground survey or an airborne survey are usually very high. Drones can help to reduce the costs by, for example, introducing platforms which can stay airborne for not only 20 or 30 minutes, but maybe hours. One of this is this fixed wing UAV. It's an existing technology, and we are already writing a proposal for a major mining company to use it for wide area imaging of the electrical conductivity. This aircraft can stay 3 hours airborne and can carry 5 kilograms at an average speed of 100 kilometers. So production rates up to 500 kilometers and more are possible with such an aircraft. Another trend is that over the years, exploration projects were progressively exploring under deeper cover. So in the early days, only a few hundred meters were achieved. But now there are projects which need to see at least 1,000 meters deep and deeper. So we need to adjust our applied geophysical methodologies to get to this depth. Next, due to the climate crisis, new technology shall be introduced in the next decade or 2 decades, which requires a lot of commodities to become exploited. For example, it is expected that in the next 20-25 years, the amount of copper required, or the demand for copper, will be the same of the amount that was produced in all history. So currently we need more exploration to satisfy the demand for several species. And last but not least, here you see the periodic system of chemical elements. I highlighted the elements which are needed for high-tech products like cars and solar panels and windmills. And I think it's very hard for geophysicists to invent a methodology that allows to identify directly these elements. But I think it's a time to think about to focus our methodologies in a way that allows to address these elements. For example, there's a difference. High-tech countries or the industrialized countries need different types of metals than emerging countries. So in order to address this trend, I think geophysicists have to think about modification of their methodologies to address these trends. Okay, thank you.
Well, thanks very much, Johannes. That was absolutely brilliant. I have to step in because Max has got another appointment, so I'm going to be fielding the Q&A. And we've already got a decent number of questions rolled in, which I'll read the question out, Johannes, so it gets into the record, and then you can answer it. I've got a load of questions of my own, but I'll let the audience ask their questions first. So the first question is from Bill Thurmer, and he has two questions. Have you tried suppressing noise from the drone by using any EMF blocking, like a Faraday cage or fabrics designed to block EMF? And the second question, have you tried MFAM sensors?
Hi, Bill. Good to know you are there. Yeah, I think we have to intensify the our research to identify or to understand much better the source of interference from drones on our sensors, because this will be the fundamental work to invent methodologies to fully cancel out by 100%, to cancel out the noise, which would have a strong impact on the integration work of sensors into drones. Yes, I try to use my metal to shield the noise from drones with little success, but I'm sure I haven't done this in a way that would not allow to cancel out it it was not successful. But of course, this is one way, but on the other hand, shielding will increase weight, because my metal means weight. Second, the my metal must be very thick in order to shield the low frequencies. So I'm a little bit skeptic about using cages or shielding material. Your question, a second question, FMG, or what was it?
MFAM sensors.
MFAM.
Yeah.
MFAM. I heard about it. Yeah.
Can you tell us what those are?
This is a magnetometer. I think it's produced by a startup company in Denver. MFAM, or maybe, yeah, MFAM. A new kind of sensor. This is, I think, optical pumped magnetometer. Very light, cheap, and maybe does a job. I was discussing with a client whether we should use it, but we are a little bit skeptic because we don't know how it differs to other existing type of magnetometers in terms of accuracy or resolution.
Okay, Dennis Woods just dropped a note in the chat that MFAM magnetometers are sold by Geometrics. So we have a couple
okay,
of
sorry.
questions.
It's a different one. Yeah, it's a Mac Arrow. It's a Mac Arrow. Yeah. Yeah.
Couple of questions now from Long Ying Chow. First one, do you get IP effects in the data collected in Norway? And the second one, for a survey in Turkey, did you consider terrain elevation when you explain the data? Or is it super near surface, so you don't care? So IP effects on the
IP
data?
effects, yeah, of course, it would be very nice if I could see them. If they are there, I'm sure I cannot see them because the EM measurements are a little bit more noisy than ground measurements. So I don't think I can identify them in the data. And I didn't try.
The survey in Turkey, terrain elevation effects.
On what?
Whether you modeled them, I guess.
I didn't model them.
Okay.
I didn't model them. I just handed over the data to the client and he did the job.
I see. Dennis Woods asks, well, first of all, Dennis says, very informative presentation. Thanks, Johannes. Please describe the line of sight limitations at the Turkey survey and how it was overcome. Have you carried out any drone EM surveys using a ground transmitter loop rather than a dipole source? And then finally, so a cheeky one, who digs up the UXOs and how? But, you don't need to answer that one.
Sure. Okay. I'm very tired. So the first question was
the line of sight limitation.
The line of sight. In Turkey, we tried to get permission to fly line of sight, and it's tricky in Turkey. We had to ask the governor of this part of the country, and he was officially informed, but we never got a clear answer. But it was so remote, so far away from everywhere. So we tried it. Yeah, we flew beyond visual line of sight.
And Dennis's second question is one I was actually going to ask as well, and that was whether you thought about using a horizontal loop source.
Yeah, on ground.
On the ground, yeah.
On the ground, no,
yeah.
Not yet. Okay. Yeah. And a third, who digs out? Yeah.
The UXO.
Yeah.
I mean, that's the German military, I'm sure.
It's okay. You need to be in Germany. You need to be a certified person to dig it out. So the problem is the company who engaged us, which is a big German defense in the defense industry. They asked several companies to fly over a test field, and we were selected because the accuracy of our location was good enough. It was better than 0.5 meter. You know, if you fly a drone, you have to deal with a lot of errors, not only the noise, but also navigation and everything. And if you hand over a map of suspicious anomalies, which do not with very bad with a bad X and Y accuracy, it's not fun for the person who digs it out. He has to search for it. He knows there is something, but it takes him a lot of time to dig it out. So we were selected because we were so accurate. Yeah. And we can do even better now because we have developed a system which allows to be in the range of 50 millimeters now.
Yeah, I'll ask, there's 4 more questions, but we're already 1 3/4 hours in, Johannes, so I'll just ask one more question. And that is from somebody who's anonymous. Could you clarify how you perform positioning of the mag sensors with multi-sensor gradient measurements, separate GPS for separate mag sensors, or the fixation is rigid?
Yeah, it's difficult to have a rigid, to fix sensors rigid to the drone, because then you have problems while takeoff and landing. Yeah, there are 2 ways. Either you have a one GPS on the drone and navigation unit on the boom, yeah, which also records the movement of the boom. Or you have 2 GPS, very light GPS sensors, both on the ends, both ends of the boom. Yeah.
Okay, I'll use my prerogative as a host to ask one question of mine. 7. Is there any move to start using fleets? Because you see all these fabulous fleets of drones doing all sorts of pyrotechnics with position control. Could you not use fleets of drones, each drone carrying a single mag or a single EM sensor, and then you can get the gradient?
Yeah. Last year, I was invited by UGCS in Latvia, who provides software for geophysicists, for drone geophysicists. And they gave a presentation of using 10 drones simultaneously. Yeah. Technically speaking, it's not a problem anymore. It's just a matter of bureaucracy. Yeah.
Brilliant.
Because
well, I'd like to.
Bureaucrats want to have 1 pilot per 1 drone, not 1 pilot and 10 drones.
Yeah.
But technically, it's possible.
Yeah. Well, I'd like to conclude by again thanking you very much. A completely enthralling presentation, Johannes. Brought everybody up to date. There was 50-odd people online, and I'm sure hundreds will watch this over the next months. And so this recording will be online as soon as I get it from Zoom, and the Johannes's presentation will be on the Antinet. The recording will be on YouTube. And so anyone with questions, and there's some questions we didn't get to ask, please send them directly to Johannes, and I'll be very eager to address your questions. Again, thanks very much, Johannes, and I hope to see everybody next week.
Okay.
Bye for now.
Thank you very much. Have a great day.
Bye.